I'm live on. Okay. Hearing.
Questions here. Lights.
Yeah. Everybody's there? Nobody's there, I think. But people think nobody's there, I think. कोई है ही नहीं. Hello, everyone. Anybody is there? Oh, okay. So those who are already come, for this live session, would you kindly introduce yourself through the chat? So welcome you all. Please write down your name and just say from which place you have come and what you are doing. And I hope you are all enjoying this course. Very useful and important course, especially for inorganic chemistry people, advanced transcendental chemistry, right? Yeah, so the chat box is active. Okay, please write your name. So that when you are asking question, I can call your name and, they are not writing. Yeah. Oh, maybe they were not hearing. Hello, can you hear me? Can you hear me? Okay. Hello, everyone. Can you hear me? Those who are present. Okay, good. Jay, Apurva, Pragati, Bhavel, Rajat. Oh, good. Okay, so let me know what are your questions. If you have any doubts or you need any clarification, please feel free. Hi, Sakshi. So no matter how good or how bad the question is, okay, you have almost 45 minutes to bother me. Okay, keep asking, the questions so that you have in your mind. Please write down your question. Let's start, maybe with J. You have any question? Apurva? Okay. So there was a question about assignment. Huh? Okay, assignment 3, question number 7 or 9? 7. Okay, this is about magnetic moment of hexa aqua iron 2 complex. Okay. And what is so for this one, magnetic spin only magnetic value is given. You have to talk about total stabilization energy. Crystal field stabilization energy you have to calculate. That means it's a hint to tell you that this complex is okay. 5.92. What does it mean? It means a plenty of unpaired electrons are there. So that means you can write either high spin complex or low spin complex. In most of the cases, divalent metals, if they have 6 water molecules in its coordination sphere, to assume octahedral geometry, okay, then it must be a high spin complex. Okay, you have to write, okay, dxy, dyz, and dxz, okay, lower energy level, and then dx minus y square, and start adding one electron at a time. And then after completing the electronic configuration of that neutral or ionic species, you count how many unpaired electrons are there, and then you know how to calculate spin-only value. So that spin-only value is given. The moment you look into the spin-only value, you come to know without any hesitation, and you can conclude without any hesitation that the species is high spin complex. Okay, so then calculate the value, that is it. The value is also given. Okay, that is minus 0.4 delta octahedral. Okay, so you try at home again. So it's very simple. So there is, oh, okay. Sir, I have a doubt in assignment 2 question. Okay, what is that question number 2? Question number 2, in which assignment it is? Assignment 3 or assignment 2 questions? I have it. Okay. Apurva is asking assignment. Uh, okay. Assignment 2 question. What is that question, Apurva? Can you write down the question? At least briefly, so that we will understand. We'll dig out that one. Yes, okay. You are talking about electron count, right? So in electron count, we have 2 methods to do electron counting. One is ionic method, other one is covalent method. Covalent method or neutral method. Okay, in neutral method, what you should do is you should not worry about the oxidation state of the metal. Okay, in that case, if you have anionic ligands that we know already, such as hydrogen, chlorine, bromine, iodine as iodo or something like that, in that case, they will be contributing only 1 electron towards the metal to ligand bond formation. Okay, in the neutral method, they become anionic only when they take an electron from the metal. Okay, Cl dot becomes Cl minus when the metal gives. When the metal gives, metal becomes plus. So in the neutral method, we are not touching the electrons on metal at all. Okay, if D5S2 is there, we are considering 7 electrons from the metal. For example, manganese, D5S2, right? 7 electrons. In that case, Cl is there, you have to count 1 electron. H is there, 1 electron. Methyl group is there, 1 electron. Whereas for neutral ligands like triphenyl phosphine, carbon monoxide, water, ammonia, you have to count 2 electrons. So this is how you do it. And then later, what you can do is, this is by neutral or covalent method. In the second method, that's ionic method, you should know the nature of the ligands. If the anionic ligands are there, you add 1 electron. Okay, so that many electrons will be taken from the metal. So then after counting how many anionic ligands are there, okay, or what is the overall charge, you can arrive at the oxidation state of the metal. Okay, say +3. In that case, okay, if you consider +3, and if you have hydrogen, chlorine, bromine, or methyl group, then each one will be giving 2 electrons. And then the metal, instead of D5S2, if it is +3, it will be giving 4 electrons. So this is how you should do it. Okay. Is that clear for you? Okay, this question is 5, assignment number 3. Assignment 2, question number 3. Question number 5. So, of course, I answered, okay, email for everyone you must have seen, okay. Among the following, we asked which is having square pyramidal geometry, but we designated only one in the answer, that is pentacyanonickelate. Actually, cobalt pentacyanocobaltate is also a square pyramidal molecule, okay. So if you, in case if you have written cobalt, okay, you will be getting marks. If you have written nickel, also you will get the marks. Instead of these two, if you have written something else, you will not get any mark for that one. Okay. Yeah. For that question, I already answered through email. Okay. Okay, this is about iron silver complex. Okay, if you look into copper, silver, and gold, okay, if you take diamino silver or diamino gold complex, in that when what happens, it is usually cationic, monocationic. That means it is in a +1 state. You know the electronic configuration of D9 system, D9s2. Okay, and then what happens if the one electron goes? All electrons in the d orbitals will be paired up. So you have D10 electronic configuration. If you have D10 electronic configuration for copper group, it will be copper 1, silver 1, and gold 1. So in this case, what happens? You have only, you don't have any orbitals left in that d orbital. So you have to consider only s and p, and especially in case of silver and gold, what happens? Orbital size increases. When the orbital size increases, okay, the overlapping will be more, and the energy difference between the higher orbitals will be less compared to the lower orbitals. In that case, they come closer to each other. Okay, in that case, in order to reinforce the bond, okay, with ligands such as ammonia, what it does is instead of going for linear geometry, simple SP means is S and PZ. When you take PZ, okay, the symmetry matches for DZ square. It is considering S, PZ, and DZ square. Okay, all three combined together to generate two orbitals which are disposed at, okay, 180 degrees. Okay, something like this. Okay, they are empty now. They take 2 electrons each from ammonia to have a linear geometry, and this is quite true in case of strong field ligands, strong field neutral ligands, when they are approaching, okay, silver to give a 2 coordination and have linear geometry. So SPD, this is a rare example where 3 orbitals, atomic orbitals, are combined to give 2 molecular orbitals, okay, hybrid orbitals. For that, 2 ligands will be giving 2 electrons each, ammonia. So they will be having linear geometry. And of course, how do you know? You might ask question, how do you know? And this comes from photoelectronic spectroscopy data and also from DFT calculations. From that one, and also the bond distance is unusually little shorter compared to having just simple SP geometry. And also the position of DZ square is also slightly disturbed in the complex compared to what it was in free silver plus ion. Okay, so all this relevant evidence is there to prove that it is SPD. Okay, is that clear for you? Yeah, I think that question was asked by Muskan. Muskan, is it clear now? And if you still have doubt, you can ask me. No problem. I shall tell you again. I shall explain it again. So Ruby Verma, you have a question? How to prepare for exam? Jay Patel is asking an interesting question. How to prepare for exam? Okay. So you should not study. If you want to, take up chemistry as your profession, you should not worry about exam. You should try to understand the subject. Once you understand the subject, no matter how questions are, twisted, you should be able to answer very easily. So the basics should be understood. How to understand basics? You have to go through, okay, periodic trends, periodic properties in detail. And also you should know what actually happens, okay, when I add an electron, when I, remove an electron, and what is the electronic configuration, and which group it belongs, whether it's 3D, 4D, or 5D, okay, how many electrons are there, and if more electrons are there, whether they repel each other, okay, how to tackle that one. So all these things comes into picture. Once you understand that and you start, explaining yourself, okay, facing any question that's given in examination would be rather easy, okay. As I said, if you really love chemistry and you want to take up chemistry for your profession, okay, you should not worry too much about exam. Instead, you should try to understand the subject, okay. Uh, and you should be thorough with physical chemistry, organic chemistry, and inorganic chemistry, okay. And once when you put your knowledge into understanding, okay, each and every topic you learn in chemistry, it becomes very easy, okay. And also what you should do is go to two books. One is CS Housecraft book, uh, okay, and other one is Atkins and Shriver book in organic chemistry. Go to each section, each chapter, and look into all the problems, okay, and you should be able to solve all the problems. Once you could be able to solve all the problems, and also look into worked examples, and worked examples will guide you how to solve problems given in the exercise at the end of each chapter, okay. And otherwise, if you don't understand, come back again and start reading, okay. And if you start reading, it's not that you cannot understand, some lethargy comes into picture, okay. And if ready-made answer is there somewhere, okay, you will not try to solve yourself, but instead of looking for answer, okay, try to read one chapter and paragraph related to that one and try to start answering question. You should be able to do that. Once you answer all the chapter end chapter problems from these two books, you should be able to answer any question, okay. That's simple. Is that clear? Pragati is asking, sir, pattern of exam. Pattern exam you must have seen already. Again, pattern you should not worry. There are all multiple choice subjective questions. But subjective question, it doesn't mean that you should simply looking into the four options and eliminating. Instead of eliminating, if you have time, try to solve it and confirm that the right answer you are taking. Okay. And sometimes you may see one or two ridiculously wrong answers, okay. That if you could do it, at least there will be some questions where you can do it quickly, and some questions needs some workup, so those you have to spend more time. And of course, if you have already solved some of the problems, or if you have listened to my lecture thoroughly and look into the examples I have solved, you should be able to pass this exam very easily. It's in fact, inorganic chemistry is much easier. Hope you agree with me, right? Yeah, you're right, Rajat. If you have one or more unpaired electrons, it has to be paramagnetic. And if you don't have any unpaired electrons, okay, it will be diamagnetic. Yeah, absolutely right. Hmm? Okay. Well, Mn, okay, if you just look into that's a MnCN8 4 minus. Okay, so that is a homoleptic. Okay, homoleptic molecule. Homoleptic molecule means you have only one type of ligands. Okay, for example, molybdenum hexacarbonyl, tungsten hexacarbonyl, iron pentacarbonyl, hexa-aqua, okay, hexacyano, pentacyano, all these things where you have only one type of ligands, they are called homoleptic complexes. In homoleptic complexes, what you should think is, unless there is some John-Taylor distortion you can anticipate because of okay, unsymmetrical filling of electrons in the T2G orbital. Okay, if it is not there, even if you don't see weak John-Taylor distortion, okay, molecules tend to be symmetrical and to have a higher symmetry. Okay, In that case, what happens? They will adopt, okay, a geometry that can have centrosymmetry. That's the first thing. If the molecules prefer to have a symmetric geometry, okay, then they should prefer, if there is an option, they will prefer to have a geometry which has centrosymmetry. So from that point of view, okay, again, it's not only that, okay, further, for example, square anti-prismatic is there. How square anti-prismatic will come? You take a square prism. If you take square prism, it is something like this. Or one layer you twist it at 45. Then what happens? It will be staggered. When they are staggered, if you start connecting the edges, okay, from one plane to another plane, you will end up with 8 triangles, equilateral triangles. And you have above and below, you have square face. Okay, otherwise sides, you have 8 equilateral triangles. Okay, now on above and below, you can have 2 axial ligands. Okay, then that will be bicapped square anti-prism. Okay, so but in here, if you have only 8 coordination, okay, you can have dodecahedral geometry or square anti-prismatic geometry. So here, yeah, I think here correct answer is dodecahedral geometry. Because if you consider dodecahedral geometry, okay, it's very simple. I have taught you how to arrive at geometry, okay, and how crystal field splitting for various geometries, including linear, hexagonal, planar, hexagonal, all those things. In the same way, what you do is take dodecahedral geometry, okay, and you put 8 ligands, okay, in that fashion, and then after putting 8 ligands in a dodecahedral environment, then you place all the orbitals, okay, metal orbits, okay, S and P. Of course, don't worry about S and P. You try to take dxy, dyz, and dxz, and other 3. So when you place them, you just see how much deviation is there from that one. On the other hand, you put square anti-prism, okay. So then you should be able to tell, okay, which geometry it prefers. Okay, so that's very simple, and also based on that one, you should be able to tell, okay, which orbits it is using, okay, if you go with hybridization concept. So when you learn the art of combining hybridization concept with crystal field theory, okay, you will come up with ligand field theory, and once you go to that one, okay, you should be able to tell what is the preferred geometry for a molecule or a species, ionic species, if we have an option. Same way it is true in case of square pyramidal as well as trigonal bipyramidal. Okay, square pyramid doesn't have center of symmetry, trigonal bipyramidal has, but again, it depends on what kind of electronic configuration you have. Okay. Yeah. So please merge the for every week's lecture, and also please give the assignments related lecture. Well, most of the assignments are based on what you are learning in that particular week. For example, 12 weeks course is there, 12 assignments are there. The assignment is done in such a way as questions are, okay, taken in such a way that all the questions belongs to that particular. Okay, little bit variation can be there, but most of the questions are set in such a way that they deal with the chapters that you are dealing or the lectures you are dealing in that particular week. Yeah. Okay, this one is, see, the question itself, it says it follows 18 electron rule. Okay, the moment we say it follows 18 electron rule, and if 3 metals are there, okay, you should account for 54 metals, 54 electrons. Okay, 18 into 3. Okay, right? And so you have to account for 18 into 3, 54 electrons should be there. Okay, of course, if less number of electrons are there, you have to consider metal-metal bond. Okay, in case of a 3 metal system, each metal can have 2 metal-metal bonds, right? So you have to consider those, and then you have to calculate Cp is there. Okay, you go with both neutral method as well as ionic method, and if X is given, X has to be, it doesn't say specifically, X has to be anionic ligand. Okay, X has to be anionic ligand. Okay, in that case, nickel is there. Nickel is D8S2. and Cp is there. Cp is in the neutral method is 5 electron. In the ionic method, it's 6 electrons. And then CO is a neutral. That means each metal, if you take each metal, 1 Cp5 and 8 electrons are there. 8 plus 2, 10 electrons, right? D8S2, right? 10. 10 plus 5, 15. 15 plus 1 CO. 1 CO is for all. Okay, so that means you cannot take that. Is it only 1 CO?
Three chemical bonds, and there are two COs.
Exactly. So yeah.
Like
Yeah. So two COs are there. Okay. So that means basically what you should do is take nickel, 3 nickel are there. So you have 24 electrons. Okay. 24 electrons are there, right? And then you have Cp 15 electrons are there. Let me do it. Okay. For you. Oh. Who's this? Ravi? Oh. I keep forgetting. Boom. Hmm. Hmm. Yeah. The question is Cp3, Ni2,
three.
Ni3, CO2,
And this is mu3 CO, sir. Bridging.
X, right?
No, sir, there is no X.
There's no X. Okay.
CO is mu3, bridging.
Yeah. Okay. So yeah, here hint is also given here.
Right. Yeah, still.
Yeah. So you have to calculate charge. Okay. Okay. So yes, if you consider this one, nickel has D8 S2 electron configuration. So 10 electrons are there. Okay. And then Cp, each one 5 electrons. So here 30 electrons plus 15 electrons and plus 4 electrons. Okay. So 49 electrons are there. Okay. It should have 54. Okay. So because it is 18, if it satisfies 18 electron rule, it should be this one 54. So now how much deficiency is there? And two metal-metal bonds three metal-metal bonds you can consider. Okay. So 3 electrons will come, right? 3 electrons will come. And then the charge will be 2, right? Oh, 6. No, 6 will come. Yeah, yes, yeah. So this I should not consider now. Okay, so, but each one is giving only 1 electron. You have to give only 3 electrons. Okay. No. Yeah, so then it will become more.
So charge is +1, no?
Okay.
So it will be +1.
Okay, yeah, okay.
It's 55.
55, okay. If it's 55, see, what you need is 1. That means you have to get rid of 1 electron. Okay, so that means basically it should be, the Z should be equals positive charge. Okay, so now you put here. Now I will go back, put plus here. Okay, now go for ionic method. Now, when you go for ionic method, what would happen? This one will be 18, and then later we will remove that one. So this is 30, and this is 6, and this is 1, right? Yeah, no. This is not 30 because 3 electrons are going. Okay, 3 plus 1, 4 electrons are going. 4 electrons are going means it's basically you remove this one here, 26. Okay, so now it will be 54. Okay, so now if you consider the structure, it will be like this. This is already given, mu3. And then we have bond like this. Okay, metal-metal bond. Then we have so this is the structure. Okay. So you have 3 metal-metal bonds are there, and 2 COs are bridging all the 3 metals. So you have mu3 CO, and each one is coordinated in like this. Okay. So now the charge is plus. Okay. This is how you should be able to calculate the charge. Is it clear for you? Oh. Yeah. Mm. Mhm. But I have a difficult determining geometry point compass. Yes. See, it's not very difficult to determine the geometry of a given complex if all the ligands are defined. Okay. If 5 ligands, as I mentioned, actually I have given a list of various complexes having geometries starting from linear to up to tri-cap triangular prismatic geometry. Okay, when you are doing that one, you can do from 2 approaches. One is from valence bond theory. Of course, valence bond theory is not a complete theory, but it can give you some hints certainly. And then you can go for crystal field theory, and then you combine both of them and go for ligand field theory. Okay, that we call it molecular orbital theory. First you should do is you have to determine the type of ligands you have and the nature of the ligands. Okay, whether they are positive ligands or negatively anionic, cationic, or neutral, and then how many ligands are there. And then after looking into that one, if everything is perfect and is a homoleptic molecule, for a coordination number 6, most preferred geometry is octahedral. You can go for octahedral geometry and then put them. Once after putting them, okay, you can also see by electronic configuration whether all the bonds are equivalent or not. Okay, if there is a discrepancy or unsymmetry in the T2G, okay, so then you have elongated one. So you should be able to do it and start working on. Take some unknown complexes are already known in the literature whose geometries are well defined, and start understanding and start writing some molecules of your choice with some ligands, and you practice it, it will come to you. Okay. See, several complexes are given. Okay, one is very similar to Wilkinson catalyst, where instead of PPH3, we have trimethyl phosphine. So ligand is okay. Ligand number is same. In all cases, we have 4 ligands are there. Okay, one is rhodium complex, one is a gold complex. In case of gold complex, it is gold 3 plus, and the rhodium 1 plus. Okay, I will write down those complexes for you. Again, I think here. Huh?
This power points.
This one?
Below power point is it?
Oh, this one. Yeah. Then this also blocks, right? Good way. So 4 complexes are given. One is okay. Next one is AU. Okay. L4 minus PDCl 4 2 minus
Iridium, CL,
iridium
CL,
Cl
PME3 worldwise.
PME3. Okay. Yeah. If you consider all these ligands, all these complexes, okay, 4 coordination number equals 4. And of course, when coordination number is 4, you have 2 options. One is tetrahedral, other one is square planar. Okay. And then if you just look into this one here, this anionic ligand, so rhodium is in +1 state, and AuCl4 if you T anionic, so 3+. And then again here, palladium 2+, and iridium +1. So in this case, what happens, you know that this is D7S2, and this is D9S2, and this is D8S2, and this is also D7S2. Okay, because you have cobalt, rhodium, and iridium. They are all same. So now if you take one electron, it becomes one comes, it's a D8 system. And this also, this becomes, if you take out 3 electrons, it becomes D8. Okay. D8. And then this is also D8, and this also D8. So, okay, when electronic configuration is D8, and we have coordination number 4, so invariably, all of them will be having square planar geometry. Okay, so that means here, which is tetrahedral, right? So, yeah, which is tetrahedral. But now, if you consider here, you have to consider gold. Okay, in case of gold, also it's D8, right? Yes. Yes, it is D8 system. In case of gold, the preferred geometry for no, all are square planar here. It's all square planar. All are square planar. Yeah, you thought it is tetrahedral, right? No. Okay, here, this already has come, this question, assignment. Okay. No, here, since all of them have D8 system, okay, all have square planar geometry. Okay, you know that if you start writing crystal field splitting, okay, what happens? You have dz square orbital has 2 electrons. When it has 2 electrons, ligands approaching along z direction miserably fail to establish a bond because of strong repulsion between the ligand electrons and the metal electrons in the dz square. As a result, these 2 ligands will not come, and it has to have only 4 ligands, so it will be having a square planar geometry. Okay, so in all these cases, I think that is assignment is wrong, I believe. So AuCl4 is also square planar, and this also square planar, this also square planar, and this also square planar. Okay, so all of them are square planar. Okay, not tetrahedral. Okay. AU plus is tetrahedral. Okay, no, that's incorrect. That's incorrect. That is square planar. Okay, yeah, it has to be AU1. Okay, it should be 3 minus. If it is 3 minus, it is tetrahedral. Okay, it is tetrahedral. Otherwise, AU3 plus is square planar. Okay, is that clear for you? Yeah. There it says square planar, right?
Yeah.
What you said? No, yeah. Okay. Is it clear? Okay. Oh, yeah. Let's see. So consider this complex here. So silver, you know that it has D9 S2 electronic configuration, 4D9 5S2. So I'm writing only D9S2. It means 4D9 5S2, and then it's plus 1. So now it becomes 1 electron is gone, and then it becomes a D10 system. D10 system. So if you consider, so inner orbitals, inner d orbitals are not available. So then you have to consider this 5s and 5p, and 5d is there. Okay, now when two ammonia are coming, so approaching silver ion, what it does is it combines 5s, 5p, 5p, it preferably takes 5pz. And then when you are considering 5pz, there is not much energy difference is there between 5pz and 5dz square. Okay. So now S is there or empty. So all these orbitals, okay, S, pz, and then z square, they're all, okay, combined together to form two orbitals. So something like this. Okay. They are called SPD. And then your metal is sitting here, okay, having empty orbits here. These are empty orbits, two empty orbits. And then ammonia comes here. Okay, it forms a linear complex like this. So by doing this one, what happens is it strengthens silver to nitrogen bond. Okay. So this is how you can explain sp2 hybridization. Is that clear for you? Suhasini and Sonali, is it clear? Why that happens is the energy of dz square and pz, there is not much difference is there. And when you consider them, they have a sort of overlapping is there. So since symmetry is very similar, they can combine with, of course, S is symmetrical in all direction. So they combine together to generate these sp2 orbitals. And then they are disposed at 180 degree. And then 2n ammonia will come and approach to form this linear molecule. What is the next question? Any questions you people have? Just stop sharing. So Hassan, is it clear? So you might ask me, how do I know that it's SPD? This is a very special case. It's only for your knowledge. Certainly, I would not ask. In case if it is asked, certainly that clear option will be there to tick that one. Okay, and these are all the rare cases where we see very unusual hybridization. Probably, the exams are conducted not to not to make your life miserable or anything, just to see to what extent you have understood. Unfortunately, in a subjective, okay, question set, unfortunately, we cannot judge about those things in many questions. But if it is descriptive, you can always write, and sometimes you can get even 75% marks correct, even if you are wrong in arriving at the right answer. But on the other hand, unfortunately, in case of the subjective, we have to consider, okay, right or wrong. So that's where these problems will be there. That's the reason highly complicated questions will be avoided. And in case if highly complicated questions are given, they are specifically discussed in the class, okay, in the lecture. Okay, so that's the reason, give full attention to the lecture, listen to it. Only 30 minutes, 60 lectures are there. Okay, and if you listen it carefully and follow it up with solving some problems from those respective chapters of those two books I told you, you should be able to understand and answer all the questions. And also, I suggest you people to take the exam. Okay, if you take exam instead of just registering for the course, that helps. Okay, that helps what kind of questions comes, and that probably that might help you in taking up GATE and CSIR exams as well. So from that point of view, you get a practice, and also you will get to know what kind of questions are there, where similar questions might come in CSIR or GATE. So take it seriously and answer. I'm sure you can save a lot of money going to the coaching classes. Okay. Okay, you're asking something. Okay, how to relate or how to integrate. So organometallic chemistry, when we talk about organometallic, you cannot, it's coordination chemistry when it is extended to ligands having metal to carbon bond, and if the carbon species can be anionic or neutral. So that's essentially organometallic chemistry. Okay, when you have nitrogen, instead of nitrogen, you replace with a carbon fragment. It can be neutral or anionic. Okay, phenyl group, methyl group, ethyl group, isopropyl group, or you have some carbonyl group, okay, ketonic group, all those things, if they are anionic or neutral, okay, once one such ligand is there, we call it as organometallic compound. And in most of the catalysis, what we do is, what we look into is organic transformation, okay, organic synthesis. Ultimate aim is to make a CC bond. Okay, that's what we do in organometallic chemistry. Either making a CC bond, either making a CO bond, either making a CN bond, either making a CS bond, or hydrogenation. We do not go beyond that one, right? So that means essentially we have to have, okay, catalysts for organic synthesis. Organic synthesis, we have conventional method. There are hundreds of name reactions are there, and some of them also go through homogeneous catalysis, and most of them go through homogeneous catalysis, and there are some system that goes through heterogeneous catalysis also. For example, petrochemical, hydrocarbon cracking, all those things are there, okay, and to make smaller molecules and all those things. And if you consider catalysis, 86 to 84 to 86% of catalysis what we use in organic synthesis comes from heterogeneous catalysts, and only 16 to 17% is homogeneous catalysis. That means there is enormous scope is there to bring down, okay, the drastic conditions to perform reaction under milder conditions, okay, and also if we have some functional groups to protect them, we go for homogeneous catalysis, because most of them are carried out at low temperature, less than 200. In case of heterogeneous, we go for 600, 800, and all those things. That is surface catalysis. Okay, surface catalysis. Okay, so heterogeneous catalysis, surface catalysis, there also it's likely that you'll be forming organometallic species, okay, at high temperature. Okay, but it's basically cracking. Okay, so cracking means, at high temperature on the metal surface, CC bond is broken. And then if the CC bond is broken, it's essentially, it will form two carbon fragments, they will bind to the organometallic species and they come out. So organometallic compounds invariably there, whether you say heterogeneous or homogeneous. But in case of homogeneous, you can have well-defined intermediates, and you can trace them, if not isolate them, using various spectroscopic methods, and spectrometry is there, mass spectrometry is there, and spectroscopic methods are there. Okay, you can use these as a tool to identify them in the in situ, in the reaction solution, or sometime you can do excess reaction under ideal conditions, and you can isolate them, and you can even do crystal structure. So that's the advantage with homogeneous catalysis. Homogeneous catalysis, you can arrive at exact mechanistic path that is followed during catalysis, whereas in case of heterogeneous, it's a bit difficult, because at that high temperature, you cannot really identify any of those species. Okay, it's a bit difficult. Nevertheless, you get the product at the end. And to understand kinetics and reaction mechanism, you have to go for homogeneous catalysis. That's a major difference between them. Nevertheless, heterogeneous catalysis rules the organic synthesis. Okay, is that clear for you? Well, I'm retiring from, IIT Bombay. Otherwise, I would have taken happily. Unfortunately, you should know that, hundreds of, students like you are writing, and we have a scheme where top 1 or 2 students, okay, maybe top up to 4 or 5 students, can get scholarship to come to IIT Bombay to do research. Unfortunately, not in my lab. Okay, if some other course are there, you can go. On the other hand, okay, in case if you have a desire, we have a summer internship scheme. Look into our R&D web portal and just see, okay, whether you can, you can get some scholarship or you're eligible for that scheme, and you have to go for it. Otherwise, what best is learn all those things systematically, pass CSR exam, okay, good rank, and pass GATE exam with good rank, and then hunt for a better place, okay, when the advertisement comes for PhD interviews. That's all I can say. Venkat, Rao, anything else? So I wish you all the best. So do well. As I said, if you really want to take up chemistry seriously in your professional life, okay, to do PhD, or if you are doing BSc, MSc, or even MS abroad or somewhere, so learn, okay, the basics, understand the basics very clearly. So that should take you, okay, a long way in achieving your goals. If Okay, another 2-3 minutes are there. If you have any questions, you ask me before we close this session. Sonali, you have any question? Sohasini, Kirti, Vasanti. Oh, Vasanti is from our side, I think. Sakshi, Pragati, Maskan. Any more questions? If no more questions are there from your side, shall I say goodbye? Or shall I wait for 2 more minutes? I will wait for a couple of more minutes. Okay. Just think about that. Still you have time. If you have any questions, you can bother me. Okay, I did mention, in the beginning, I think 2 important books are there. Of course, Advanced in Inorganic Chemistry by F.A. Cotton, 6th edition is a very good one. If you want to know more about classification of ligands, okay, we have plenty of examples as in the first 400 pages. You have plenty of examples are there, and very interesting chemistry is described there. But if you want to learn basics in a very clear, crystal clear manner, go for inorganic chemistry by Atkins and Shriver and Atkins book, and another one is by Housecraft, CES Housecraft. I prefer 2nd edition CES Housecraft. That is, PDF is available online. Okay, you can just download it and read. Very good book. And if you have an opportunity, buy that book. That's a very interesting book. That is. So these 2 books are very good to understand most of the concepts we come across in inorganic chemistry. CES Housecraft, and who is that? Constable and Sharpie. Yeah. If you type in Google Inorganic Chemistry 2nd edition by Housecraft, it will take you directly to that book. Okay, and probably you can download PDF of that when it's available on web, Google. So how many lectures are over now?
6 weeks. 15.
Okay, so almost halfway through. Okay, we are halfway through. Probably I will take one more live session sometime in September. Okay, until then, have an excellent time reading and enjoying chemistry. Okay, and in case if you have questions also, you can bother me. Okay, my email is there. Okay, certainly I would answer your questions. Okay, I wish you all the very best. Thank you so much. Okay, good. Yeah, at least more.